I can't speak what other tests, test books that are using a small ki erroneously. Okay, so if that is the case, then we have to go by the lecture in this case, because small ki's always refer to forming a permanent covalent bond. Maybe for any kind of reflection of how well an inhibitor binds to the enzyme is only reflected by a big Ki. Okay. The break constant tells us how fast it binds. Okay. There's always a rate constant of how fast any molecule binds to the enzyme, and that can be the inhibitor binding the enzyme. But that small k is not small k big I. The nomenclature is for permanent covalent bond formation. Number 21 talks about the penicillin. In this case, penicillin form a covalent bond with another amino acid residue and not a serine residue. And in that case, then it was considered to be an affinity inhibitor. And that is true because of what we understand how the penicillin inhibit the enzyme. Penicillin inhibit the enzyme by fooling the enzyme for the first step of reaction. The first step of catalysis is to use a serine residue to do the covalent attack to form the transient covalent bond. The fact that penicillin can trigger the catalysis and form that covalent bond that eventually not being broken, then it qualifies that to be a mechanism-based inhibitor. So in other words, if the covalent bond that is formed that is not catalysis dependent, then it would just mean that the penicillin resembles the substrate, binds into the enzyme active site, and then form a covalent bond without dependence of the catalysis. Then it will fit more so as an affinity inhibitor than a mechanism-based, simply because mechanism-based has to go through catalysis. So in this case, then, if you still remember, I said penicillin is not that clear on example as the suicide inhibitor, and this question actually addressed that. Yes. Okay. The affinity inhibitor usually have a good leaving group, because that's how you can form covalent bond, right? So if you look at the penicillin structure, actually, because of that amide bond, it is a good electrophile. It's open up. Just that the leaving group never leave the molecule. Yeah, it's open up, right? So it's not like something leaving, but then it is a good electrophile there because of the ring structure. So then it's sort of like, if you look at penicillin, the first thing people might assume that it is an affinity inhibitor because it is reactive. Because usually mechanism-based inhibitor is not reactive at all. But if you look at a beta-lactam, it is somewhat reactive because of the spring structure. The question is that can we tell if this affinity inhibitor if it is binding to many proteins, but not just that protein? Is that what you mean? Okay. In the notes, it says the affinity inhibitor can bind to any protein. I hope that was not what I said. So the affinity inhibitor whenever you add a molecule, you're going to have protein surrounding. It can interact with surrounding molecules. So because it has a good leaving group, if the non-specific interaction is close enough, there's a nucleophile, you form a bond. So that's what I meant by, like a molecule with a reactive group, it can react to many things. Anything is in a solution. But what makes it a good affinity inhibitor is that it has affinity to specific molecule, enzyme. So then, yeah, you're going to bind there, but then most likely it's going to find this one and bind. So that is affinity inhibitor then of some value. But then, by definition, all affinity inhibitor has a reactive group, right? So then, by definition, you're going to have lots of side effects. Because anything that you keep in contact, you'll modify. But there's no good binding affinity for other things. Inhibitor X resembles structure of NAD. Oh, we'll talk about that. So, good. We don't have to talk about this. Yeah, this is a non-competitive. We'll talk about that. Okay. Says, how do I know NADH can bind both enzyme and enzyme?
Dr. Chen? So in general, if you have a cofactor or a coenzyme like that can qualify as an inhibition, competition, like an inhibitor competitor.
Repeat your
If
question.
you have a coenzyme if you have, let's say NAD plus, like in any of the reactions, does that qualify to be a competitive inhibitor to the substrate? Any sort of substrate? Like in a case of NADH, for example.
The question is, I'm not quite understanding the question.
I'm not understanding why NADH can qualify to be a inhibitor.
Oh, I see. Right here, okay, I see a confusion. Why NADH can be inhibitor? But this molecule is not NADH. It looks like NADH. This inhibitor structurally resembles NADH molecule. Okay? So here, I think the confusion is that can it be uncompetitive? Because can it be that you have to bind the substrate first, and then NADH can bind? Not that without acetaldehyde, NADH cannot bind. I guess that would be rare, but then one of these, I think it is a fair assumption that if it is like different binding pocket of the within the active site, molecule can bind without dependent upon each other. And that was one of the reasons why I brought out citrate synthase, because one would expect that citrate synthase can bind OAA, acetyl-CoA, both of them can bind. But then it's not the case. So I brought that up to you guys. Or else, whenever enzyme active site binds different things, then it should be binding at the same time. At different times fine. If for example, alcohol dehydrogenase, then it will bind acetaldehyde, NADH, then one would expect that acetaldehyde can bind, NADH also can bind. It doesn't depend upon which one bind first. And that's why it makes citrate so unique that without binding OAA, acetyl-CoA cannot bind. So I think there's a fair assumption that if you have an enzyme that have metal ions, have NADH, or substrate ATP kinase, doesn't mean that without substrate ATP cannot bind. Usually it's not that. If it is, then it is a disease. Yes. The question is, does NADH bind at the same site, the active site, or any outside? And in all cases, because utilization of NADH is hydride ion transfer. So it has to be close proximity to wherever it is getting it. So the binding site must be very close to substrate. It has to be the active site. Now, handout number 8. But handout number 1 is the longest. This is not too long. Yes. Is that a I forgot the sample question? Okay. I think I remember the question. It is on the allopurinol as the inhibitor of xanthine oxidase. And then upon binding the xanthine oxidase active site, it's being converted as a substrate, be converted into the product. And turn out that the product has a better affinity than allopurinol. What kind of inhibition would that be? Yes. So in this case, when we say something binds better or worse, that will refer to binding affinity, the big Ki or big Km. Okay. So here, it would mean that allopurinol has Ki or Km that binds, and in this case, it is a substrate, so it has Km. So after it's bind, it forms something that binds better. So the Ki of the product is smaller than the Km of allopurinol. Okay.
So it would be mechanism based because it does form
So for the question is, why would not be a mechanism based? Any mechanism based inhibitor, number one criteria cannot have it, don't have it, is that it must have a permanent covalent bond formation. So if there's no permanent covalent bond formation in any inhibition, it cannot be irreversible inhibition, cannot be mechanism based. Whenever we qualify, when we talk describing this inhibitor binds better or bind worse, we always refer to non-covalent binding, right? Binding better, always referring to bind, stay there, not coming out, better or worse. So if there's a covalent bond formation, then it has to be explicitly mentioned. Okay, now talk about the Warburg effect. And cancer cells use glycolysis because oxygen isn't necessary for the reaction to occur, or the cancer cells use glycolysis as the option to use oxygen within the reaction. And cancer cells would rather glycolysis without oxygen. In this case, Turner-Warburg effect it applies to tumors given with oxygen. Okay. So it is a typical phenomenon that even though with oxygen somehow it will typically rely on glycolysis for making ATP, and that's kind of strange. In this scenario, so it is a lot easier to conceptualize in the solid tumor that has a hypoxic core, that oxygen is limited, and that's why it would use glycolysis to make ATP. But the more that we know about the cancers, a lot of times, even though in the presence of oxygen, the enzymes in glycolysis is upregulated. And then the enzyme prefers to use glycolysis for ATP. So it's kind of something that we do not fully understood at this time. mentioned that magnesium kinase is used for shielding and also for neutralizing negative charges. Meaning the same thing, sort of the same thing that magnesium is shielding the O- of the phosphor and hydride bond, and then in this case also for neutralizing the charge and it's also for binding. So neutral and charge, so same thing. Yes. But then in enolates and the PEP reaction, magnesium stabilizing negative charge on substrate. Hexokinase, PFK stabilizing the negative charge on ATP. Is that correct? Yes. So then we can see that magnesium is used to basically for binding. In the case of kinases, it is binding with the ATP, and then the binding involves the negative charge oxygen of phosphor and hydride bond binding, and also because it involves nucleophilic attack, so it facilitates the nucleophilic attack much more so with the neutralization of charge. And in the case of enolase and pyruvate kinase, in both cases, then substrate is unusually negatively charged. So the magnesium now is using as also for binding, but not on in the case of ATP, now it's binding the substrate. So uniquely in pyruvate kinase, magnesium is used to bind the substrate PEP, and also magnesium is used to neutralize negative charge on the ADP tube for the nucleophilic attack. So it's for both, for both usages. Can you explain how PFK is a regulatory enzyme? How is that steric inhibitor? How is it? So first of all, the glutamate and arginine, these are, yes, part of PFK. So the way that the allosteric control for PFK is that either the active site has two structures. One structure has the glutamate close to the glucose 6-phosphate. So then glutamate is not minus charge, glucose 6-phosphate, phosphate is not minus charge, won't bind as well. Or it can have another conformation as arginine plus charge close to the glutamate, close to the glucose 6-phosphate, negative charge phosphate, now binds better. So it is depending on what molecule binds into the allosteric site that will confer either arginine close to the phosphate or the glutamate close to phosphate. So that's how the allosteric control occurs. So what is the step of glycolysis? So this one involves, this is a term, the only term that I talk about is the enzyme that involves the preferential TS binding. So going through the TM enzymes of the day first. So this actually sum it up pretty well, and then we see that concentration is always more DHAP than gap. So TIM is very effective to establish this concentration. So whenever there is one gap going through glycolysis, consumed, then one of them quickly go and replenish, then for TIM, it's close to 10 to the 9, and that is basically its diffusion limit. Then whenever it sees the gap in DJP, it will just reach the equilibrium.
So, question.
Yes.
So, DHAP turns the gap fast? Okay.
Say it again.
So, would that mean that DHAP turns the gap quickly?
No, the question is, does DHAP turn to gap more quickly than gap turn to DHAP? No, because they are equally fast. Just that whenever the equilibrium is perturbed somewhat, okay, in this case, most likely it is the consumption of gap, because gap is used to move forward for glycolysis. So then equilibriums always will be less gap, then forming the gap. So if there's any cellular event that somehow losing DHAP, then it's going to go that way very quickly, as quickly